Good afternoon, everyone. Welcome back. Now we are entering the technical session of today, which is based on the powered electronic devices and applications. Before we begin the event, I would like to introduce you to the session chairs, Dr. Ashish Srivastav and Dr. Ashish Mani. It is my privilege to introduce Dr. Ashish Srivastav. Dr. Ashish Srivastav is a distinguished professor and dean at Sri Vishwakarma Skill University in Gurgaon, Haryana. He is a beacon of expertise in the realm of power electronics. With a doctorate from IIT Delhi and a Bachelor of Head Research, he has made significant contribution to the power factor corrections through DC-DC converters. He allocates include the prestigious POSCO Power System Award, recognizing his remarkable work in areas of interest span from power quality improvements to smart grid technology. Now, I would like to introduce our second session chair, Dr. Ashish Mani. Dr. Ashish Mani is renowned academic and technological expert, currently heading startups at Amity University, Noida. With over 20 years of expertise in the field of quantum computing and AI specialist. He also serves as the Chief Technological Officer at D-Risk Technology Private Limited, Singapore, backed by Huawei Spark. Dr. Mani has a strong publicator and patent record with interest scanning quantum computing, machine learning, and interdisciplinary research. Before we move on to the paper presentations, I would like to request all the presenters to kindly note that the time will be 8 minutes followed by a question answer for 2 minutes. Let us begin with the first paper for presentation of the session. I would like to invite Mr. Ram Bhushan Singh, paper ID 7, to please present the paper on the screen. I would like to invite paper ID 7, Mr. Ram Bhushan Singh, to please present his paper on the topic automatic parallel self parking.
I think he has not joined. So let us call the next participant, that is paper ID 128, to present the talk on exploration of starting methods of induction motor. The next speaker, paper ID 128. Mr. Amit Kumar Chaudhary. Ms. Arpita Chaudhary.
Yes, ma'am. Pardon, ma'am, your voice is not clear.
Am I audible?
Yeah, ma'am.
Share your presentation and start with it.
Okay, ma'am. Just a second.
Uh, Ma'am, could you please do it fast?
Yes, sir. There's a connectivity problem with one of my teammates. You're waiting for him.
I think you will move to the next paper ID if they are not ready for the presentation.
Okay, sir. So, ma'am, you can do it afterwards, after we are done with the next speaker. So now I request Mr. Mangesh S. Kulkarni, paper ID 2324, to present his work on implementation and performance evaluation of international bilateral reactive power variation islanding detection technique in hybrid microgrid. Over to you, sir. Am I audible, Mr. Mangesh S. Kulkarni, sir? Paper ID 324, Mr. Mangesh S. Kulkarni. And the topic is implementation of performance evaluation of intermittent bilateral reactive power.
Move to the next dear, I think, if they are not ready.
Okay, sir. Now I request Mr. V. Kamaji Kanan, paper ID 394, to present his work on quasi Z source inverter with simple boost and maximum boost pulse width modulation techniques for PV grid connection. Over to you, sir.
Thank you, sir. I mean,
So you can go ahead.
you.
Yes, sir, you are audible.
Other means
So you can start. So you can share your screen. Uh, so paper ID 394. So are you facing any network issues or any other connectivity problem? So you can let us know in the chat box also. Okay, maybe sir is having some network issues. Moving ahead, I request Mr. Asan Kabir to present his work on the topic modeling and performance analysis of a model predictive and feedback in linearization controlled UAV autonomous quadcopter drone in 3D dynamics. Sir, you may share your screen and move ahead. I repeat, paper ID 445, Mr. Azan Kabir, to please present his work. Okay, so moving ahead. Now I request Mr. Madhvi Nirikar, paper ID 460, to present a work on GA-based optimization methods for charging of electric vehicles by scheduling the load of home appliances. Ma'am, you may go ahead.
Hello,
Yes, sir.
sir, this is Kama Chicken.
Sir, could you please repeat?
Kama Chicken, paper ID is 394.
Paper ID what?
394.
394.
394, yes.
Yes, sir. You may go ahead, sir.
Okay. Whether my screen is visible, sir?
Yes, sir.
Then, good afternoon, myself, Dr. B. Kama Chicken, Professor Electrical and Electronics in the Knowledge Institute of Technology, Salem. And then my title here it is quasi source inverter with simple boost and maximum boost pulse width modulation techniques for PV grid connection. And this is about my content that I'm going to present here, going with introduction and then proposed grid connected system, that is PUDL quasi source inverter, followed by results and discussion, and then conclusion, and then finally it is about the reference. Coming to the introduction, right? As we know, we now presently the PV system is drastically increasing. That is mainly which is connected to the grid. Integrated systems are nowadays becoming more popular, and then still we are having almost total capacity, installed capacity is more than 400, almost 424 gigahertz are there. Among that, almost 30% we have it is about renewable system. So still we are having much more technological developments in grid connected systems. So we need a proper inverter system so as to have a proper standalone system, or it may be a grid connected system. Here I am going with quasi source inverter. So it is having some several advantages like boosting capability, and then we are having here single stage inversion is possible without any additional components. And then about current input current, right? That is stress on the input current will be reduced. Again, stress in the DC source, which is also going to be reduced. So by considering all these advantages, we are going with quasi-absorption method. And then this voltage boosting characteristic is mainly helps to reduce the shoot-through duty ratio and then the TST in a three-phase system. And then it is also helps to reduce the conduction losses. So the system efficiency is supposed to be very high. So here in this paper, we are having a novel high gain partial input union output dual impedance quasi-Z source inverter, simply called PUDL QZSI, which is fed by PV system, right? Which is going to be entire system which is connected to the grid. So this is my proposed PV grid connected system. So here you can see the solar system, and then this is dual impedance network. So here we can see 4 impedance, that is inductors, and then 5 diodes, and then 4 capacitors are there. So since it is advancements of diode assisted quasi-Z source inverter, so this is coming under a diode assisted quasi-Z source inverter. And then here we are going to have 2 different types of controller. One is simple boost pulse width modulation, and then the other is maximum boost pulse width modulation. So this is the closed loop structures. Here the system which is connected to the grid. So it is a three-phase system. So we have considered here. Coming to the operating mode, so here we are having 2 different types of modes. One is shoot-through mode and then non-shoot-through mode. In shoot-through mode, under short circuit condition, that is during turning on switching the conditions. So here you can see 2 diodes. There is diode D1 and then D5, which is going to be on, and then the remaining diodes will be in off state. So this is under shoot-through state. So here we are having 2 impedance network. So during the shoot-through states, we know that the inductor which is going to be charged, and then during non-shoot-through state, the charge voltage which is going to be present in the inductor, which is going to be back to the next level. That is inverter side. So during non-shoot-through state, the diode D1 and D5 are off state, and then the remaining diodes are which is going to be diode D2, D3, and then D5, which is going to be under conduction states. So during this state, whatever the voltage stored in the inductor is going to be feedback to the next level. There is three-phase. So this is about the control structure, that is control scheme. So here we are having 3 different types of control. One is voltage control, that is MPPT based P&O voltage control, which is provided in order to extract maximum power from the solar panel. And then the second, it is grid side current control. There is IGABC stands for grid side current control. So in order to ensure the output voltage, desired output voltage. So and then the third voltage control, it is at the DC voltage control. So here a simple structure, right? Here we can see the ABC, that is part transformation, right? So 3-phase ABC frame can be converted to direct and quadrature axis, and then with the help of 2 PI controller, we have a reverse transformation in order to generate the PWM signals to the 3-leg input. So this is a simple structure. So here we are dealing with 2 different PWM techniques. One is simple boost PWM, and then the other is maximum boost sinusoidal PWM waveform. This is how the carrier waveforms and then the respective PWM pulses for each and every switches in the 3-leg inverter. So here we can see so this crossing points, right? All 6 diodes, which is going to be all the 6 devices, power devices, which is going to be turned on. So this becomes shoot-through states. Whatever the things highlighted here during this shoot-through states, in order to generate the necessary firing pulse to the 3-leg. So this is about the simulation. So here we have considered the simulation parameters of inductor, capacitor, and then the switching frequencies. And then this is about the grid side inductor, that is filter inductor, and then capacitors, what we have selected for simulation. So this is the waveform what we obtained during simulation, that is case 1. During when we are considering 1000 watts per meter squared, that is solar irradiance of 1000 watts per meter squared. So this is the obtained phase voltage and then the phase current, and then this could be your active and reactive power which is delivered by the system. So here we have considered two cases. One is under 1000 watts per meter square, that is solar irradiance under 1000 watts per meter square. So, and then the second case, it is about during solar irradiance of 700 watts per meter squared. We have considered these two PWM techniques, and then we have obtained the waveforms, and then we have checked the current TST, the split current TST, whether it is obtained within the limit. So this is the 50 analysis for case 1 under 1000 watts per 1000 watts per meter squared. So this is here the TST for simple boost sinusoidal pulse width modulation. It is this is for phase A. I'm for phase A alone. I'm showing here. TST it is 2.21, and then for another PWM techniques, that is maximum boost sinusoidal pulse width modulations. Here the TST obtained for phase A, here it is 2.14. Then, as I said, case 2 for different irradiance. So under solar irradiance of 700 watts per meter squared, this is the obtained grid voltage, grid current, and then the power, active and reactive power under case 2. So here, this is the TST spectrum for SPWM and then MBSPWM. So here the obtained TST for phase A is 2.5, and then this is for MBSPWM. Here the obtained TST is 2.36. So this is the final table which shows for all the three phases. It's the current TST under two different solar irradiance conditions. That under 1000 watts per meter squared, under TST under 100 watts per meter squared. So here here we have considered two different PWM techniques. So here when compared with SPWM, here you can see the TST obtained by maximum boost sinusoidal PWM techniques, which is lesser in both cases. They are 1000 watts per meter squared and are also under 700 watts per meter. So from this, I want to conclude here the system, that is PUDL with quasi source converter under maximum boost sinusoidal PWM techniques, which obtain TST very less when compared with the sinusoidal simple boost sinusoidal. And coming to the conclusion here, as I said, so this quasi source inverter which provides very high gain with very less shoot-through duration, and then which helps to increase the modulation index. So, from the conclusion results, in the result discussions, it is very clear. The injected current TST, which is very less when compared with the simple boost PWM technique. And then here, by analyzing just two PWM techniques, we have considered two different irradiance conditions, that is under 1000 watts per meter squared, and then during 700 watts per meter squared, we have for different irradiance conditions. We have implemented the same in the MATLAB. So from the simulation, it is proved that proposed PUDL quasi source with the maximum boost simple PWM modulation techniques, which achieves very low injected TST, that is the current TST when compared with the simple. So this is about the reference. Queries?
Thank you so much, sir. Now the floor is open for the questions.
Dr. Kamachi, I have few queries.
Yes.
One, you have not discussed the reason of selecting this 15 kilohertz frequency. why you have chosen a frequency of 15 kilohertz? This is question number 1, because normally high switching frequency we talk about more than 40 kilohertz. Secondly, in your whole discussion of this presented work, there is no discussion on the switching losses reduction and the conduction losses reduction. And what do you mean by quasi? You have not shown the quasi wave. You talk about the quasi inverter, but then the waveform output I have not verified that it is a quasi wave inverter, Z source inverter. So kindly address these queries.
Put first query on switching frequency. Usually we'll go with, as you said, it may be 30 kilohertz, more than 30 kilohertz we will prefer. But for our system, right, for based on the load, we have considered 2 kilowatt load. So based on the load consideration, we have selected such frequency.
But any justification? It's not a hit and trial. There has to be a justification for selection of certain frequency.
Yes, based on load, we have calculated that switching frequency.
Do you have any formula how you calculated the frequency on the basis of 2 kilowatt?
So we fix the load, and then whatever the paper I have shown, it is not the complete. We have not included the every equations and then the entire modeling.
But my concern is if suppose we run the system on 10 kilohertz or maybe 20 kilohertz or maybe 40 kilohertz, that maybe it may reduce the THD further below than what you have quoted. So how we can justify whether this is the optimized frequency on which you have operated the system? That's my main question. Can you please address if you have the answer?
Yes. Yes. Actually, the frequency depends on the entire device what we are selected for simulation. It depends on the load and then the what we are having in the source. So based on that, we have fixed switching frequency of 15 kilohertz.
What about the other two questions here? The switching losses and the conduction loss. There is no reduction. You talk about the reduction on conduction losses. There is no discussion on switching losses.
Yes. Actually, we have the simulation results. What we have shown in the paper, it is very less. Only 20% of the results only we have projected here, and then we have included all these things in the during publication part of next level. That is.
Can you tell me how much loss, how much wattage loss of switching loss and conduction loss in your system?
I want to check that.
And how you justify it is a quasi Z source inverter? Because I have not seen the output quasi waveform.
So that's what I am saying. The results what we have, I'm sharing in the paper, in my paper, what I have submitted. It is only partial results I have included. Maybe I will include all these things. Presently, I don't have such relevant waveforms.
But can you differentiate square wave, quasi wave? What is the difference between square wave and quasi wave?
Yes, square wave it is we supposed to have just like during conventional voltage source motor we supposed to generate. We will have a 180 degree and then 120 degree. We will have a square wave waveform. In case of 3-leg inverter, then quasi it is not equal to the square wave waveform. Partially it is a mix of square wave and then it is similar to multi-level and then pure square wave. So it is a combination of.
How many levels are there in the quasi waveform?
Yes.
How many levels are there in quasi waveform? It's a 2-level, 3-level, 4-level. How many levels are there?
It is near to 11. I think. I'm not sure. I will check that.
Chalo, and have you checked about comparison between PWM and PFM? pulse width modulation and pulse frequency modulation. Have you checked with PFM as well, running your system?
Also,
Okay, that's all. These are the questions from my side. If any other query by any other member, they may ask.
Thank you so much, sir. Now, moving ahead, we have the next paper. I would like to invite Ms. Arpita Chaudhary, paper ID 128, to present her work on the topic Exploration of Starting Methods of Induction Motor. Over to you, ma'am.
Yes, thank you. So we'll start our presentation.
So, paper ID 128.
Good afternoon, everyone. I, along with my team, Ayushi Priya and Jaivir Kumar, are going to present a presentation on the topic exploration of starting methods of induction motor. So, moving on, what is an induction motor? A three-phase induction motor has a potential to start by itself. A magnetic field is created around the rotor by a three-phase winding that make up the stator. The interaction between the magnetic field direction by the rotor and the stator, which are both rotating, causes rotation to occur. So, what a paper is dedicated to? We are dedicated on finding a efficient starting method for a paper for an induction motor. So why is an efficient starting method needed? It is commonly known that an induction motor draws a large amount of electricity from the supply when it's starting. In order to decrease starting current while maintaining starting torque, the starting technique rate is explored. They are helpful in providing protection from overload and low voltage. Before I delve into the details of our research, I'd like to explain why we decided to choose this particular topic. The decision to investigate how to reduce the high initial power draw of an induction motor while maintaining starting torque. We explored various starting techniques that also offer protection against the overload and low voltage. So, what are our problem points? Large induction motors with their slow acceleration due to high shaft diameter risk damaging windings from prolonged high current. Our goal is to reduce the starting current, preventing heating, and protect against overloads and low voltage. Common starting methods include Star Delta, direct online starting, and auto transformers. Our work aims to find the best starting method to lower current while maintaining starting torque. Now we would discuss in details about all the three starters with the help of Simulink to deduce a perfect starting method for a induction motor. Over to you, Javier.
Thank you, Arpita. Now, I'll take you forward through the various starting methods of the induction motor. First of all, exploring the induction motor, we come across the DOL starter, that is the direct online starting. A direct online starter is a straightforward and widely used device for starting induction motors. It provides a direct connection from the power supply to the motor, applying full voltage at once. This starter comprises a contactor, thermal overload relay, a start and push buttons and stop push buttons. When the start button is pressed, the contactor closes, connecting the motor to the power supply. This results in an initial surge of current, which can be several times higher than the motor's rated current. This urge is essential to overcome the inertia of motor's rotor and initiate rotation. The thermal overload relay is a safety feature that protects the motor from overheating due to excessive current. Now, my friend Ayushi will let you go through the details.
Thank you, Jerry. As you can see on the screen, it is a model of a MATLAB simulation of a direct online starter. The components used are an asynchronous three-phase induction motor, which has a rating of 4 kilowatt, 5.4 HP. and we are using three single phase AC voltage sources to feed the three phase induction motor with the supply. Upon running the simulation, the following graphs were obtained. The first graph is the graphical representation of rotor speed versus time characteristics. It is, as you can see, it is approximately, okay. And then we have the next, we have the graph of the electromagnetic torque versus time, and finally, the stator current versus time. You can see that the speed is around 146 rpm and the torque is very high, almost 15 newton meter. However, the stator current is also high, that is 22 ampere. Moving forward to star delta starter.
The next comes the star delta starter. A star delta starter is an electrical device used to start three-phase induction motors. It's particularly beneficial for larger motors where the inrush current during the startup can be substantial. This starter employs a two-stage process to reduce the initial surge of current. In the first stage, known as the starter connection, the motor windings are initially connected in a star configuration. This reduces the voltage applied to each winding, which in turn reduces the current drawn from the power supply. As a result, the motor starts with a lower current, minimizing stress on our electrical system. After a specific period, typically a few seconds, the starter transitions to the second stage known as the delta connection. In this configuration, the windings are rearranged to form a delta configuration which applies full voltage to the motor. By this point, the motor has gained enough speed to handle the higher current without causing excessive stress on the system.
Okay. So, as my colleague here explained, that the star delta starter reduces the voltage during the period of start. When the connections are made in star, the line and the phase current are equal. However, the line and the phase voltage are different, thus resulting in reduction of voltage at the start. We have recorded the reading in the normal run. As you can see that for this simulation model, we have provided a three-phase connection to the asynchronous three-phase induction motor. There are three contactors used, that is the main contactor or AC voltage breaker, a star contactor and a delta contactor. Initially, the connections are made in star and then it switches to delta connection in the normal run. Next up, we have the graphs for the same. This is the graphical representation of rotor speed versus time. Next, we have the graphical representation of electromagnetic torque versus time. And again, we have it for the stator current against time. Next, we have the auto transformer starter.
Thank you, Ayushi. The autotransformer starter. An autotransformer starter is an electrical device used to start and control the speed of three-phase induction motors. It operates on the principle of a single winding with multiple taps allowing for variable voltage output in and both the input and output sides of the transformer. This differs from a conventional transformer where the primary and the secondary windings are distinct. The autotransformer has several tap points along its winding, which allows for a range of output voltages. During startup, the motor is initially connected to the autotransformer at a tap point that provides a reduced voltage. This limits the initial inrush current, which is particularly crucial for large motors. As the motor accelerates, the autotransformer gradually adjusts the voltage to the motor by changing the tap connection. This progressive increase in voltage ensures a smooth acceleration without causing excessive surges.
The basic idea of an auto transformer is that it acts as a voltage regulator. In a model, we have used variable voltage supply at different stages so that the model operates as an auto transformer. The sum of all the AC voltage sources will be 230 volts. There are four contactors or breakers operated through timers to provide different tapping. The results are again shown on the screen.
So moving forward.
Moving ahead, we have the result analysis through after the simulation. Arpita, can you put it to the result analysis? Okay, so all the three methods that we discussed here have their own pros and cons. For instance, for direct online starter, the starting current is really high. However, the starting torque is also high. But for star delta starter and auto transformer starter, although the starting current is feasible, the starting torque is low. The results, moving to the next slide, we have the results of all the data. Over to you, Arpita.
Thank you, Ayushi and Jerry, for filling us in about all the three starters. In conclusion, an induction motor can be started in several different ways, depending on the equipment, cost, and motor rating. Different starting techniques are preferred. The different power system constraints may affect the choice of the best strategy. After a thorough competitive analysis of all the starting methods mentioned throughout the presentation, namely DOL starter, direct online starter, star delta starter, and auto transformer, with the help of Simulink, it is concluded that DOL starter may be thought of an appropriate way for starting the induction motor based on the work done in this paper, where an asynchronous motor with the rating of 4 kilowatt 5.4 horsepower is utilized for comparison. Before we conclude, I'd like to share the list of the references of or sources we consulted during the presentation of this paper. Thank you for your time and attention. I hope you found this presentation informative and insightful.
Thank you so much. Now the floor is open for the questions.
Well, I think it's a very basic paper where the things have been explored as far as these different starting methods is concerned. There is no as such contribution from the author point of view. I have only one query that can you tell that what is the costing of the different starting method of starters, whether dual or auto transformer or your star delta starter? Cost comparison.
So basically, for a star delta starter, it would take around 2.5K to produce a star delta starter, and
Actually, the direct online starter is the we can't give the direct like in amount the cost comparison, but it can be said that the direct online starter is the most economical and is the best for the usage when it comes to small loads. Coming to Star Delta starter, it is in comparison to direct online, it has a higher cost, and it finds major applications in the major industries today. And auto transformer starter is has a more cost compared to the other two.
But why then star delta starter is preferred in for the industrial load, industrial machine load?
So the Star Delta starter is preferably used for industrial loads because, as you can say that in industries we are like the loads that are being used are very
so
because in
basically,
Star.
it is because it takes a less amount of current, and in industries there are high amount of current is withdrawn. The star delta obviously reduces that, so that's why it's
So it is
preferred in
more
industry.
economical. It is when it comes to industries, it is economical and it is preferred for that load that is being used in the industries.
At the time of starting, normally, how much current draws by the three-phase induction motor as compared to its rated current? How much it draws during magnetizing inrush current?
I'm sorry, sir, I cannot get you. Please, you repeat
During a
it.
starting time, during transient time, how much current draws by the three-phase induction motor as compared to its rated current?
So it is 8 to 10 times more compared to its rated current.
Fine, fine. That's all. That's from my side. Others may ask the query if they have.
So, am I audible? Yeah.
Yes, sir.
So my question is, did you try for AI methods for starting of induction motors, for a smooth starting of induction motor without much transients?
No, sir, we have not actually explored the AI concept for the starting of induction motor.
I mean, the earlier query could have been answered. It was on novelty. You would have included some AI methods or investigated some AI methods also along with the conventional methods for starting of production motors. Please consider it for future work. Thank you.
Sure, sir.
Sure, sir, thank you.
Thank you so much, sir. Next, I request paper ID 435 to present his work on AGC of two areas non-reheat power system using GWO technique. Over to you, sir.
Hello.
Yes, sir, you are audible.
Good afternoon. Hello, sir. Hello.
Yes, sir, you may go ahead.
Okay. The title of my paper is Automatic Generation Control of Two-Area Non-Reheat Power System Using Gray Wolf Techniques. Introduction.
So, could you please turn on your camera?
Sir.
Sir, could you please turn on your camera?
Okay. Is it?
Yes, sir, now you are visible.
Okay. Introduction. In order to produce and transmit reliable power at the lowest cost while maintaining the two key power system parameters, voltage and frequency, within predetermined limits, a power system interconnected control action has been integrated in various areas. Modifying the rotor angle minimizes the variation of active power, which in fact frequency. Load frequency control manages real power, control system frequency, and enable interconnected system operation. The LFC operations are used in an interconnected system to maintain constant frequency to a tolerable level and dispatch the load among generators, as well as to help control the tie line power exchange scheme. Additionally, because the LFC loop depends on the governor's speed regulation, any change in the load could cause the frequency in the steady state to deviate and possibly not return to the fixed point. Therefore, using a controller is a means to get out of this peculiar circumstance. The controller will track the over the time and inaccuracy in addition to adjusting the offset. According to stochastic theory, the variation in the load from the demand side will cause the generator to automatically change to fit in order to return the frequency to the predetermined level. The automatic generation control is the name given to this control method. In order to achieve least cost and effectively manage the area control error to steady state, it is therefore possible to interpret the role of AGC as a regulatory one. From the foregoing, it is clear that the main goal of the AGC is to produce the least amount of steady-state error, which can be done by using a basic linear controller in conjunction with simple or traditional tuning. The increasing demand on linearity and reliability requirement of our system have made simple controllers inadequate. AGC must adopt dynamic and minimize steady-state error, requiring intelligent controller and optimization tuning techniques for real-time speedy control. Literature review. Those are the related works. In Ram and et al. In a paper titled Comprehensive Review of Recent Strategy on Automatic Generation Control and Load Frequency Control in Power System. In this article, it provides an in-depth analysis of the recent development of various control strategies and their implementation concerning frequency and power control in automatic generation control system. The design of secondary controller is an important aspect of AGC for effective automatic generation control system operation. Various optimal control theories, such as conventional optimization techniques, heuristic, meta-heuristic optimization techniques, and their utilization in AGC to get the optimal performance of secondary controllers are described in detail. The recent developments include the increasing importance of various control strategies, the design and implementation of various secondary controllers, the application of optimal control theory, and various performance index criteria and its key features are highlighted. Then various performance index criteria, such as conventional and modified fixed, are also briefly explained. Finally, this paper concludes with an emphasis on controller design application of various optimal control theories and various big use in field of AGC. In another paper by S. Chatterjee and et al., automatic generation control of multi-area hydropower system using moth flame optimization techniques. The work investigated the AGC mechanism of three-area hydropower system model for its effective compilation owing to two different types of input load perturbations. To improve the dynamic response profile, installation of PID controller has been done in individual area of the steady power system model. In H-Tank et al., in a paper titled Automatic Generation Control of Power System Using Deep Neural Work, these optimization techniques have shown substantial improvement in AGC performance of power systems, leaving behind some drawbacks. Those have been further rectified by some other applied techniques. The possibility of exploring some new hybrid optimization technique is still prevailing for the benefit of AGC performance, especially by the way of optimal tuning of controller gains. Therefore, it is justified that optimization techniques may be significantly explored in AGC domain and might become an integral part of design of AGC controller. The difference between AGC of multi-area and that of single area is that only the off frequency of each area, but also the net power interchange via tie line may also be restored to nominal value. So a composite measure called AC is taken as the variable interest. Then the study also provided a superior control performance response compared to using the GA, PSO, and the PID controller equipped power system. The performance investigation of the proposed algorithms starts the AGC study, two-area power system non-linearity effects, whose stability and robustness study are also carried out. The potential benefit yielded by the proposed algorithm are compared to other techniques for similar power system configuration. In another paper by area improvement in automatic generation control of two-area electric power system via a new fuzzy-aided optimal PIDN FOI controller. It cultivates good quality of power supply via preserving area frequency and tie line power oscillation following consumers' load demand disturbance. The controller designed for AGC of power system should display excellent disturbance rejection expertise. Hence, in this study, a maiden attempt is made to propose a fuzzy-aided integer order proportional integral derivative with filter fractional order integral controller for AGC of multi-area power system. A fuzzy logic controller can handle discrepancy in the system parameters. The dynamic performance of the system can be enhanced by FLC aided optimized classical controller. The selection of FLC parameters like input-output scaling factors, shape of membership function, rule-based etc. is an intricate task. Typically, they are preferred based on few empirical rules and frequently are not the best. The incorrect selection of those parameters may influence the system performance badly. Hence, different optimization techniques have been fruitfully employed to choose the best parameters of FLC. Further hybridization of FLC with classical controller at output enhance the performance of FLC amazingly in comparison to classical controller working alone. A novel meta-heuristic evolutionary algorithm called ICA is used in this paper for current tuning of several games of the advocated controller. Research methodology. MATLAB software is used for development and simulation in this study. Precisely the power system put forward for investigation has been formed in MATLAB Simulink platform, while the PID controller has been tuned with GWO algorithm via MATLAB software. The purpose of implementing the controller is basically to consider this error term and change it into proper actuating signal so that the error can be minimized with change in time. The PID controller is a robust and versatile controller that uses fast, present, and prediction of future error to calculate the suitable actuating command of the system. That is why it is the most prevalent form of feedback controller over a wide range of power system operation. The term PI and D perform the function of minimizing the magnitude of time to raise as well as error of steady state and increase the stability respectively. Though if applied to the AGC of the system, it will enhance the dynamic performance of the investigator system. However, satisfactory operation of PID controller needs.
I think sorry to interrupt you. Are reading throughout. Can you present your work where waveforms and you may have a comparison of the optimization technique, whether gray wolf optimization or maybe whale optimization? This is simply don't read the slide. That doesn't give any information as such. Whatever your work you have done it, your contribution, your novelty of the work that you present.
Okay, sir. Shall I go to the?
Yeah, you can go to the slide where you have done the your own work.
Yes, sir.
Comparison, because you have chosen gray wolf optimization. There are many optimization techniques are available for optimizing the certain parameters. Okay. There is a whale optimization in basic GAPSO. Then there are n number of optimization techniques are there.
Okay, sir. So I
gray
should start
wolf optimization. So why you have chosen gray wolf optimization straight away?
Sir, because of its robustness.
Well, others are also robust. How you say that this is the only robust? Whale optimization is robust, and Kalono is also robust. Teaching learning optimization. There are a number of optimization techniques are there.
So going by the nature within which the gray perform its activity in real life.
Most of them are nature inspired only.
Yes, sir.
Most of them are nature inspired only. Any logical reason for selecting the gray wolf optimization for your work?
Sir, logical as in?
Any logical reason why you have selected or why you have not made a comparison of two optimization which can show the comparison that which has performed better in your case?
There is comparison table, sir. Yeah.
Comparison of the gray wolf with one optimization with the other optimization, not the KPKI and the area 1 and area 2 I'm talking of.
Okay. So because of its speedy action in controlling the error, the frequency error while the machines are in operation.
All works in the similar manner, dear. There is a prey, there is a predator. They are targeting, they are fix up the target and they take a new position. So that is the objective on which they work. So you complete your presentation.
Okay. Proposed gray wolf optimization. The AGC operational investigation uses dynamic optimization to determine control parameters. Natural inspired techniques are used due to their adaptability, comprehensibility, and ability to avoid local minima. Grey wolf optimization draw inspiration from the leadership structure and hunting strategy of grey wolf, a graceful and social predator. GWO computational and operational simplicity allow it quickly converge toward the optimum, making it effective in solving engineering problems. GW are elegant social predators with strict hierarchy. Wolf leaders, subordinate, and scapegoat play a crucial role in the pack hierarchy. If not a subordinate, they dominate and cater to the pack in their own way. The stages of GW hunting are highlighted. Then the results and discussions are as you have said to several times. Here, the performance of GW techniques is verified using two cases, robustness and dynamic comparative analysis. In the first case, the dynamic behavior of the model to a wide range in one of the vital parameters of the system, specifically governor time constant, is investigated. While in the second case, GWO technique results obtained in this study are deliberated and then juxtaposed with other techniques like PIGA and so on, and PID-based GA. Then dynamic analysis. The model of an interconnected two-area system shown in Figure 2 with model specification presented in Appendix A is considered for the investigation of automatic generation control, along with classical PID controller. Consequently, in this research work, the GW algorithm has been implemented for the purpose of optimizing.
I think, gentlemen, sorry to stop you. You are just reading the slide. That's not advisable. If you have any outcome, you please show those outcomes.
Okay, sir. These are some of the outcomes. The PI-based transient comparative analysis of investigated technique of change in frequency 1 of area 1, change in frequency of area 2, then the tile line power. Then these are the KPKD of the two areas using various optimization techniques. Then these are the robustness analysis of the GWO and other algorithms. Then these two tables are showing the transient specification of two area non-reheat linear power system. Then the other one is for the tie line. Then these are the graph for the change of frequency, area 1, area 2, and tie line, which shows plus or minus 25% variation in the time constant of the governor. This is for the tie line. Then the conclusion. In this study, dynamic evaluation of two-area interconnected power system using GWO tool is presented for AGC study. The system considers its linear non-reheat thermal model. First robustness inquiry was carried out to the design two-area model, and GW technique proved its flexibility by lessening oscillation efficiency despite variation in an important parameter of the system. Then the dynamic characteristics of the model was investigated and juxtaposed with other techniques well established in the most current literature of the model. However, GWO technique stand out to establish its high performance by converging quickly and proving its superior performance as contrasted to the illustrious technique found in the literature. Therefore, the technique can be utilized as an effective tool for optimizing AGC of power system. Thank you.
Thank you so much, sir. Now the floor is open for the questions.
I have no query, dear.
Okay. Dr. Ashish Mani, sir, do you have any questions?
No, thanks.
Thank you, sir. Moving ahead, next I request paper ID 460 to please present her work. Over to you, ma'am.
Thank you, sir.
Yes, sir. Sir, my screen is visible, sir? Hello?
Sir, my screen is visible.
Sir, actually, it's turn for the paper ID 460. Yes, yes, ma'am, your screen is visible. You may proceed ahead.
Okay, good afternoon all.
Sir, paper ID 7, sir, you said.
Sir, you are after this.
Okay, sir. Okay, thanks.
Good afternoon
Ma'am,
all.
you may go ahead.
Myself, Madhvi Nirkar. I am here going to present a paper on geo-optimization method for charging of electric vehicles by scheduling the load of home appliances under the guidance of Professor Bhanupratap sir and Mukherjee sir. So here are the contents of my paper. So basically, I am going to means my work is going on the charging and discharging of electric vehicles. So now in recent year, the electric vehicles are going to be popular due to their environmental advantages and advancement of battery technology. So the the increasing increasing EV demand for efficient charging, there must be need of efficient charging infrastructure to support the growing number of EV on the load. So the major issue for EV is the very simultaneous charging of multiple EVs and coupled with the energy consumption of home appliances, it causes the challenges for the electricity grid and necessitate the effective load management strategies. So there is extensive research has been conducted for this charge scheduling of EV. So here I am going to consider the optimization techniques, that is genetic algorithm for the scheduling of EV charging. And here I am doing the integration of load scheduling for home appliances. Means while we can charge our EV in our home. So, what are their advantages, challenges, and future research in this direction that I am going to discuss.
Excuse me, ma'am.
So, yes, sir.
Ma'am, could you please turn on your camera?
Yes, sir.
Could you please turn on your camera?
Yes,
Yes,
sir.
ma'am. You may go ahead.
Okay. So this is the scheduling of EV charging. So while we are considering the scheduling of EV charging, we have to consider these three factors. That is environment. So in environment, we have to consider the dynamic pricing, that is the real-time pricing, critical peak or and what are the tools we have to use while scheduling the EV charging. So we have to use the optimization algorithms. So algorithm is based on the mathematical solutions and implementation of optimization algorithms. So there are various methods. So out of that, here I am consider the genetic algorithms. So this is the flowchart of genetic algorithm. So this is the basic flowchart of genetic algorithm, where we have to consider the initial population, then we have to consider the fitness function, then selection, crossover, mutation, and if you achieve your best solution, or if you get your optimized solution, then you will end. Otherwise, you go for the iteration. So actually, it is an iterative method. And what is the goals of this optimization method? That is, we have to minimize the power loss, voltage violation, peak demand, energy cost, and maximize the use of renewable energy sources in the contribution of our power grid. So these are the some references which I have considered for my work.
So in some paper, they have used the hybrid GI approach for optimize both EV charging and home appliances of load scheduling. So they are demonstrated improved energy efficiency and reduced charging. In some cases, this optimization involve the multiple objectives. So cost minimization, load balancing, user satisfaction, and in the reference 6, they have using the GA-based charging algorithm that considering the charging demand of EVs and the power consumption of home appliances. So it also achieve the load balancing, reduce charging costs, and optimize the charging. So this is my problem statement. So whatever the problems are there while we are doing the charging the EV in load scheduling of home. So here we have to consider some common problem, that is the peak demand management. So wherever the demand is peak, so that time we have to do the that management. Then load balancing. So at a time there should not be any stress on the grid. And lastly, user preference consideration. So it depends on the users whether in what time we have to charge that vehicle, so that we optimize the cost. So here we have to consider the geo optimization for optimal time selection of EV charging in load scheduling of home. So this is the main target of my work. So here I am considering the means one data, that is the list of the home appliances along with their scheduling detail. So in that I have considered the appliances, various appliances start time, end time, so and duration and their cost. So and this will be give the energy consumption over means for a day. And here in table 2 is give the different tariff intervals and corresponding unit price, which is in dollars. So here I have shown the various intervals, their starting time, end times, and what is the tariff will be decided for that particular period. So this information is essential for developing the load scheduling algorithm that aim to optimize the overall energy consumption and cost efficiency of the system. So again, our motto is same, that minimize the electricity cost. This we have to consider this. Now, the objective function is that the minimum T cost is defined by this objective constant, that is summation I equal to 1 to n, summation j equal to 1 to m, bracket 1 half, again bracket summation um, P equal to 1 Sij into Pj into Ci. So I have used this equation. So where T cost represent the total cost of energy consumption to be minimized. It's summation of the cost calculated for each appliances and time interval. N defines the number of appliances. T defines the number of time intervals. So here I have taken the half an hour, means from 11 to 11:30, 11:30 to 12. So for 24 hours it is 48. And here M is the number of tariff intervals. So already I have shown. So I have considered the 5 number of time intervals. Then Sij represent the energy consumption of the appliances during I. Here for I during time interval T, for tariff interval J. And here Pj is the price of electricity for tariff interval J. And here Ci is the cost factor of the appliances. So whatever the data I have shown in that table, that I have considered. So the here again the main target is to optimize the reduce the overall cost of the energy consumption while considering the tariff intervals and appliances specific cost. That is, whatever the cost of that appliances for that energy consumption means for that particular period. So this system utilizes geo-optimization approach to find the optimal scheduling solution. So these are the results. So this scheduling of EV charging. So here see on x-axis, is it visible? So here the time interval is for and half an hour, and these are the various appliances. So in the morning time where the demand is less, so during that time here EV will get going to be charged. So this illustrates the optimized EV scheduling during the morning hours, gives that the minimum load occurs in both the morning and evening period. So whenever the demand is less, that time we are going to charge the EV. So this is the graph, and this is the uh, this fitness curves. So it initial load curve without use of GA result is the least favorable fitness position for the minimum load. So after running that program, here I get this graph which shows the best fitness and worst fitness value. So here you can see from this graph. So x-axis defines the generation number of generations, and y-axis defines the fitness value. Now from figure 5 means whatever the data I have getting from that data I have done the analysis. So figure 5 demonstrate the optimal load curve achieved through the application of the GA, which lead to the best fitness position from the minimum load. So here our target is for that minimum load, we have to get the best fitness value. So here genetic algorithm is used for determination of best and worst fitness, which relies on the parameters such as number of generation, population size, mutation rate, and crossover rate. So these are the four parameters that we are going to we have to put that values, and then we are getting the different best value and worst value. So, however, during the program execution, we have to select the parents and offspring, and leading to the fluctuation in the best and worst fitness value over the time. So, only for a few iteration here we get some fluctuation. After that, we get the constant value. So here you can see this horizontal line. So then again. Here we have considered the different number of population, and we get the minimum and maximum cost, that is best value. We have run that program so many times, and here I get this result of geo-optimization across various population sites. So the box plot showcase in the result in response to changes in population size can be found, that is here. So so this illustrates the performance of GA is identifying the optimal solution for EV scheduling under the different population sizes. So here you can see by changing the different population sizes, here we can get the optimal solution. So population size displays the highest variance, indicating the sensitivity to initial conditions.
Oh,
So
excuse me,
here,
ma'am. Ma'am,
yes,
could you
sir.
please conclude?
Yes, sir.
Ma'am, could you please conclude?
Okay, sir. Sir, only two slides are remaining. So this is again one load profile which we are showing. That blue line indicate when we are running the program, means when we are load consumption without genetic algorithm, and red will be showing the with genetic algorithm. So here you can see you get the various number of values, so that in that position you can charge your EV, and you can minimize the charging cost. So this is the conclusion. So geo-optimization method play a significant role in enabling the optimal time selection of EV charging in load scheduling of home appliances, and leading to improve the energy management, cost saving, and enhance user experiences. So in future research, I am focusing on integrating the renewable energy sources, or considering V2G capabilities, or explore to other meta-heuristic optimization techniques. These are my references which I have referred for this paper. Thank you.
Thank you so much, ma'am. Now the floor is open for the questions.
Yeah, I have a one question, Madhavi, that why you have not considered load scheduling for 12 p.m. night to 6 a.m. because this is the least load period. You have considered up to 11:30 p.m. in the night.
Sir, my program, actually my program is done for it's 11:30 to 12:30 to 1. So that's why I have considered.
No, but you can. It is you who have designed the program, and everyone knows that midnight till 12 till morning 6 or 7, the load is the minimum load.
Yes, sir. We can.
That the
do
charging
that
can
also.
be for electric vehicle. This is the most optimum timing for the charging.
Yes, sir. We can do that also.
But in your work, it has not been reflected. So that has to be taken into consideration. Everyone knows that the 12 to 6 is the load period, which is the lean period of the load.
Yes, sir.
That's
Means,
all. That's all from my side.
Okay, sir.
Okay, Dr. Ashish Mani, sir, do you have any questions?
Yes. How many variables do you consider for optimization purpose?
What, sir?
I mean, it appears to be a combinatorial problem. So, how many variables were there in your final problem formulation that you considered for optimization purpose?
So basically, here I am considering the cost. Whatever the consumption cost
Cost
is there.
is your objective function, but
Yes.
how is it changing? What are the variables, that decision variables that you have considered? How many of them are there? Because that defines the complexity of the problem.
Sir, actually, it depends on the whatever the consumption of that appliances is during that period that I have considered.
Okay, thank you.
Okay, sir, thank you.
Okay. Now I request paper ID 324, Mr. Mangesh S. Kulkarni, to present his work. Over to you, sir.
Good afternoon.
You may proceed,
Shall I
sir.
continue? Yeah,
Yes,
thank
sir.
you very much. Good afternoon to one and all. I'm here presenting my research, research work based on the implementation and performance evaluation of intermittent bilateral, along with my research guide, Dr. Sachin Mishra and Dr. Suresh Kumar. This is my outline of my presentation. So in the starting, I would like to introduce the importance of the demand of the energy nowadays.
I think I request to the author or the presenter, you
decades.
please come to your work. The journal thing or the introduction you can may skip.
Okay. Sure, sure. So I have considered one of the problem or issues of hybrid AC/DC microgrid. So there are a lot of operational challenges with regards to the operation of AC/DC hybrid AC/DC microgrid. So what I've considered is operational load transfer challenge, in which islandic detection I've considered for my research work. So as per the IEEE standards 1547, the condition in which the part of the power system becomes isolated from the rest of the network, and having at least one DG is called islanding. Whenever there is islanding, the DG source which remains in the power system continues to supply to the local load as well as to the utility grid. So my motivation behind the research is it will cause the danger to the maintenance and installation personnel. Then the distraction at the both the customers and utility side equipments. It also impact to the power quality as well as it will worsen the operation of the utility breakers. There are lot many methods which already has been there in the research, or which researchers already worked on these methods. So the methods are broadly classified into conventional islanding methods and modern islanding detection methods. In the conventional, we have the remote and local, and in the local, we have the active, passive, and hybrid islanding detection method. In the modern, we have the signal processing and intelligent-based islanding detection methods. So the system which I have designed in a simulation is in front of you, which consists AC microgrid and AC microgrid. Combined is called as a hybrid AC/DC microgrid. On the left hand side, I have included the supercapacitor and the fuel cell, and on the left hand side we have the utility grid. It also consists a 10 kilowatt diesel power plant, 22.22 kilowatt wind power plant, as well as the energy storage devices like supercapacitor and fuel cell. It also includes the solar photovoltaic plant of rating 27 kilowatts. The generic the detection technique which I have considered is the active ionic detection method, and the method is bilateral reactive power method, which is the intermittent. The left hand side flowchart shows the generic working of the any active method, where the disturbance is injected at the PCC, that is point of common coupling. Then after, there will be a threshold for the set parameters at the PCC. If that threshold parameter is going to exceed, it will be sent signal to the breaker, which will isolate the microgrid from the utility grid. The method which I have considered is the bilateral reactive power variation method. So according to the requirements of the IEEE standard 929 and IEEE standard 1547, the quality factor needs to be considered is 2.5, which I have included in my study, as well as the maximum and minimum frequency range is from 50.5 Hertz to 49.5 Hertz. The power which, the reactive power which needs to introduce into the system, which is been calculated by QDIS with the help of maximum and minimum frequency, quality factor, and the rating of the DG connected. So under the normal operating condition, the voltage, under the normal operating condition, the voltage profile, I have missed this. Actually, this one is wrong. With regards to frequency, the BRV is signal to the current regulator and islanding detection signal. So if we just pay attention to the islanding detection signal. So under the normal working condition, the detection signal, there is no detection signal from the system. And the frequency is also working at the rated value. In an islanding detection, whenever there is islanding, the frequency exceeds its threshold values. And initially, the BRPV signal which has been activated, which will introduce the reactive power into the system, as well as it will retrieve the reactive power from the system. Whenever there is the frequency threshold exceeded beyond the specified rated values, the islanding detection signal which sends to the islanding breaker, which will isolate the microgrid from the utility grid. Along with this, I have tested my islanding detection technique with the 3 tests. The first one is large load switching test. The large load, which is of 60 kW, is connected to the grid system, and which is switched on at the 0.35 seconds. So as there is no impact onto the, there is no activation signal from the particular designed islanding detection method. This method suits even when there is a large load switching in the power system. Then there is a nonlinear load integration test. 12 kilowatts of nonlinear load is integrated in the system, even though the designed detection signaling system is not detecting the islanding, which is expected. Finally, I've compared my results with the existing islanding detection techniques, which are of active type. So what results I've got is the non-detection zone for the proposed system is 0, as there is equal amount of power reactive power is introduced into the system and extracted from the system. There is very negligible error detection ratio, and there is very negligible impact onto the power quality of the system, which is less than 3%. I can conclude from my study, the suggested method can detect the islanding very quickly by setting threshold parameters very correctly, which will eliminate the non-detection zone and preventing nuisance trip at the same time. And it also having very negligible impact on the power factor as well as the reactive. There is no introduction of harmonics in the system. Thank you, sir.
Thank you so much, sir. Now the floor is open for the questions.
Mangesh, I have a query that
Yes,
going for once the situation of islanding arises,
yes, sir.
then how much time you have not shown that for re-establishing the power as well as maintaining the power quality?
Sure, sir. So my what system or detection method I've designed, which will detect the islanding within 63 milliseconds, and then it will restore the islanding part, and it will disconnect the utility grid.
Okay, that's all from my side. Thank you.
Yes, thank you, sir.
Okay, Dr. Ashish Mani, sir, do you have any questions? Okay, moving ahead. Next, I request paper ID 7 to please come and present his work. Sir, you are not audible right now. I repeat, next, I would like to call upon paper ID 7 to please come and present his work.
I think you may call 445, which is the last one. He is finding difficulty in connecting.
So your screen is visible. Now you may proceed. Sir, you are not audible.
Sir,
Sir, may I audible, sir? Hello?
yes, you are audible. Please start your presentation.
Yes, ma'am. Ma'am, my presentation is automatic parallel parking car, which is based on embedded system. So, ma'am, our stack the new automatic parking algorithm we developed. We in this algorithm we use Bluetooth through parking our vehicle, so that how it's work. Here the Arduino HCR which sensor technology for designing artificial park RP. The system which use the system Arduino microcontroller to process data from our ultrasonic sensor and Bluetooth module to communication mobile. So through this in a vehicle we In vehicle, we set up HCR0 sensor, ultrasonic sensor, which is used to detect the object through this. And after this, we use Bluetooth module. Through if we in Bluetooth app, we select parking zone, so that our vehicle automatically get vacant space through in the that space. It's automatically park our vehicle, sir. Sir, advantage and disadvantage of this, sir. Advantage, sir, there is a high parking efficiency. A self parking car can fit into most driver can manage on their own. This make it easier people to find parking and allows the same number of car to take up fewer space, sir. And the disadvantage, as the mechanism involve high technology, it's too high cost, but the parking system are usually automated but required to regular maintenance to ensure everything working smoothly. Please, sir. How is sir, our circuit is like that, sir? Sir, it's visible, sir. This is our circuit.
Yes, sir, it's visible.
Yes, sir. So here we use Arduino Mega, sir, and 3 sensor which is used, sir, HCR0 ultrasonic sensor, and here we module, and here this one is the red one, sir, motor driver. And the problem is, sir, the problem is address invention. The invention address of driver who struggle with parking, particularly in busy urban area where finding a can be challenged. Parallel parking can be difficult for many drivers, and this can lead at the even. So, detailed solution, sir. This is here, sir. The automatic parallel self parking car with Bluetooth technology provide us a solution to problem by automating the parking process. The car sensor and the camera system detect the available parking spot the car to self park. Sir. The result, and here's a prototype car have been designed. A prototype car has been designed in this paper that automatically determine parking space and perform parallel. The car used manual control to find parking space and drive roads. On the vehicle organize a specific location. Its algorithm start working after receiving the command from the driver, which is we send a command through Bluetooth app. So if we in that app we select like that, sir, I show you. So this is the which I command we made on the Bluetooth app. So here this is the parking one and the forward, backward, right, and stop. And this one is the parking slot. So if we click on this parking slot, it's automatically find the space and self park. So this is our system. So and here is the flow chart of so we start and receive after the receiving from the command. So reverse into the parking space. If we available, not available, so then it's working. How like it's. So here our conclusion. The prototype of our system is involved in automatic system that perform parallel parking procedure to find empty space, and then the station is parallel. We also use an RC motor in our system to which we add hardware component such as microcontroller, DC motor, servo, DC motor, and for ultrasonic sensor in this system. In the car search of the free space, and if we find is less than the required space, the car continues searching the parking algorithm. However, if the length is empty, slot is greater than the certain size, then motor stop after the system is simulated, implemented, and the test the results so that we can successful out of the task. Sir. Here are, I have also videos, sir, in this related to. So thank you, sir.
Thank you so much, sir. Now the floor is open for the questions. Dr. Ashish Mani, sir, do you?
Yes,
Yeah, please go ahead, sir. Sorry, the floor is open for the questions.
I have no query, dear.
Okay, Dr. Ashish Mani sir, do you have any question?
So, what is the novelty in your paper? I mean,
Sir, in my
yes, please go ahead.
sir, in my novelty in paper, sir, we add Bluetooth, sir. Through Bluetooth, we park this vehicle, sir. In Bluetooth, we add HC05, sir. Through this, just like in there is
Has got
another
a
one
very limited
project like that, Bluetooth control.
Yeah, but Bluetooth has
What,
got
sir?
limited range, right? So,
Yes, sir, I know, sir. But yes, sir, I know Bluetooth has some limited range, but because of this, we sir implement hardware things also. So that sir, it's a prototype, so that we implement, sir.
okay, thank you.
Yes, sir. Okay, sir. Thank you, sir.
Thank you so much, sir. Next, I request paper
Sir, may I
ID.
leave, sir?
Sir, could you repeat?
Sir, may I leave, sir?
So you may stay in the meet.
Okay, okay, sir. Okay, thank you.
Now, moving ahead, I request paper ID 445 to please present the work. Over to you, sir. I repeat, paper ID 445. Mr. Ahsan Kabir, to please present your work.
I think no one is available from 445 paper ID, I hope.
So he's there in the meet, but maybe he's facing some network issues. So am I audible to you? I repeat, paper ID 445. So you may go ahead with your work. Not yet.
I have a meeting at 4, dear, so may I excuse to leave?
Okay, sir. Thank you so much, sir, for joining the session.
Thank you, dear.
Paper ID 445. Mr. Ahsan Kabir. So if you can hear me, you can please start. Go ahead with your work. Mr. Mohammed Bello, sir, if you can hear me, you can start with your work. हम ये है ना मीटिंग में.
I have already presented my own. It was the 435 paper.
Sir, your screen is not visible to us.
Mohammed Bello is talking. I have already finished my presentation. I was the one that presented the third paper.
Yes, sir, your paper is already presented. We are asking about 445. Paper ID 445. I think the presenter of paper ID 445 is not available. So, since all other papers are presented, I think we can end this session. So, thank you everyone. And thank you for participating in RDK 2023. And you may join the next plenary session, which is there. Thank you, everyone.